we spoke last time using this sort of strange energy diagram for describing the options available to our starting materials, which have been an alkyl halide. By this I mean some hydrocarbon attached to a halogen and a nucleophile. And the options for alkyl halides include methyl alkyl halides, which is just like methyl iodide, or primary alkyl halides, where one of those three hydrogens on the carbon that has the leaving group has been replaced by another carbon, secondary alkyl halide, or tertiary alkyl halide. Of course, I don't mean to communicate that these are the only primary, secondary, and tertiary alkyl halides there are. There's lots of structural variation possible. They don't all have to be methyl groups. But that's the idea. In a primary alkyl halide, the halide is attached to a primary carbon, and so on. The nucleophiles that we've talked about have either been good nucleophiles, where their conjugate acids have pKa's greater than 0, or poor nucleophile, good, bad, I don't know, which includes basically water and alcohols whose conjugate acids have pKa's less than 2. I'm sorry, of -2, which is less than 0. So a couple general principles. Good nucleophiles will tend to favor SN2. They're reactive enough that they don't want to wait around for the leaving group to leave. Poor nucleophiles are not strong enough to attack via SN2. Okay, so I guess we could note here, good nucleophiles will go SN2 if possible. Why do we say if possible? Hang on, we got to consider the alkyl halide. Not good nucleophiles aren't going to do SN2. That doesn't mean that they particularly favor SN1. It just means SN2 isn't an option, so SN1 is the only thing that can happen. We saw last time that because of sterics, the SN2 rate is fast for, hold on, didn't leave enough space for myself. There we sort of go. SN2 rate is fast for methyl and primary alkyl halides. It's a bit slower for secondary, and there's no SN2 reaction for tertiary alkyl halides. And the reason for that is sterics. And then one thing I think I mentioned briefly at the end of last time was we'll see that the SN1 rate is slow and in fact not really fast enough to even be possible for methyl and primary. It will be less, it will still be slow for secondary alkyl halides and will be less slow for tertiary alkyl halides. What the heck am I doing here with slow and less slow? I don't want to communicate that SN1 reactions are ever fast, because they are not. In each case, you're breaking a bond and you wait for the leaving group to leave before things can really get going. What I mean to say is, of all of the available options for a tertiary alkyl halide, since SN2 isn't possible, SN1 is the way to go. And I mean that the SN1 reaction involving a tertiary alkyl halide is going to be faster than for a secondary alkyl halide. All right? Good so far? Questions? Okay. So I want to talk about why the SN2 rate, or sorry, the SN1 rate varies in this way. And to do this, it actually might be useful for a moment to draw the energy diagram for the SN1 reaction on its own separate axis. So on the y-axis, as usual, we have energy. On the x-axis, whenever I struggle with that, I think of the scene in The Office where Oscar's trying to explain a graph to Michael Scott, and he says, yes, that is the x-axis. Michael was kind of an idiot. SN1 completeness here. Not really either of these horizontal axes, sort of its own thing. In the SN1 reaction, you have starting materials, you have carbocationic intermediate, you have products, and then we've said that there is a transition state, which we call transition state 1, because it's the the transition state of the first step, which is the rate determining step. And then products are here. Okay. So notice that the transition state and the carbocation are pretty close to each other in terms of percent reaction completeness. That means not a lot has changed as we go from transition state to carbocation. And I want to introduce a rule of thumb that can help us, because transition states, you can't actually see them. It's difficult to think about them. And so there's a principle that helps us connect the structure of the transition state to the thing that it's closest in energy to. So this is the Hammond postulate. And the Hammond postulate says this: on an energy diagram, two adjacent states, like, for example, a transition state and a carbocation intermediate, two adjacent states that are close in energy must be similar in structure. Okay. Two adjacent states that are close in energy must be similar in structure. And that is because if the reaction completeness doesn't change much from here to here, and energy doesn't change much, then geometry can't have changed that much. So two states that are close in energy on an energy diagram, and if they're adjacent to each other, must, of necessity, be similar in structure. Why do we care? Well, let's think about the structure of a carbocation. Since we're talking about SN1 reactions, let's let our carbocation be a tertiary carbocation. So this is the intermediate. Now let's consider what the transition state looks like. In the transition state, the bond between carbon and the leaving group is lengthening, which I'm representing with this dotted line. We'll put this whole thing in brackets with a double dagger to indicate that this is transition state 1. In this transition state, there's a buildup of partial negative charge on iodide as we break the bond, and iodide takes its electrons with it. At the same time, there's a buildup of partial positive charge on the carbon. Now let's consider, I'm going to draw the starting material here, and I want us to consider together how the structure around that central carbon changes as we move from starting material to transition state to intermediate. In the starting material, what is the hybridization of that carbon? sp3, tetrahedral, and in particular, those methyl groups should be separated by about 109 degrees-ish. Okay? In the intermediate, what's the hybridization of that central carbon? It's sp2, trigonal planar, and the bond angles here are 120 degrees. So they used to be closer together. They're moving farther apart as we get to the transition state. What do you think the transition state looks like for that central carbon? What do you expect for this bond angle or its geometry? Who knows, but somewhere in between, right? Not quite tetrahedral, probably not quite flat. All right? In the noon lecture, some folks were asking, why is it that the transition state is higher in energy than the carbocation when the transition state at least still has the iodide nearby and there's not a full positive charge on the carbon? Sorry about that with the recording box. I know better than to do that. Is that? No, it's still. Okay, it's gone. Sorry about that. Folks asked, why is the carbocation intermediate less or more stable than the transition state? And the answer is that in the transition state, you've given up most of the stability associated with the carbon iodide bond, but you've not yet let the methyl groups relax to the complete trigonal planar structure where they're as far apart as possible. In other words, in the transition state, you've still got residual pent-up electron-electron repulsion between, or steric hindrance between these methyl groups that are closer to each other than they would otherwise like to be if the carbon were only surrounded by three things. So the downward slide here from the transition state to the carbocation represents sort of a popping open of the carbon to a complete trigonal planar intermediate. All right. Nevertheless, in the transition state, we still have a fair amount of positive charge at the carbon. And so we're going to say that the transition state is carbocation-like. Again, who cares? Well, now we've got something that we can actually think about because organic chemists know a fair amount about carbocations. They can be studied, they're intermediates, they can be observed. We know what makes carbocations stable. And so, therefore, what makes a carbocation more stable also makes the transition state more stable, which also accelerates SN1. Let me say that again. Because the transition state is carbocation-like, if this dot represents the position of the carbocation, and if we know how to do things to make the carbocation more stable, then we are also going to stabilize the transition state and make the reaction faster. Yeah? Does it affect the activation energy? Yes. If you stabilize the transition state without doing much to the starting material, then yes, energy of activation is lower, rate constant is higher, rate is faster. All right, other questions? Yeah.
So SN2 will be slower, or does it not change?
SN2 will be slower under what circumstances?
Under the circumstance that you stabilize the first transition state?
Yeah, well, in general, we haven't yet talked about how to do that, but we're going to see that tertiary carbocations are more stable than primary. So yes, increasing the amount of groups on the carbon that has the leaving group will tend to lower this transition state and this intermediate and make SN1 faster. And that same change, because of steric hindrance, drives up the energy of the SN2 transition state. Yep. What else? Okay. So let's talk about carbocation stability now. The stability trends follow pretty precisely with the SN2, or I'm sorry, the SN1 rate trends for the reasons we've just talked about. Did I press cut there? I didn't want to cut. I just wanted to copy. There we go. So we'll erase this SN2 column here. And we'll make another column for carbocation stability. Least stable for the methyl carbocation. We generally won't write the methyl carbocation as a reasonable intermediate in solution phase reactions in organic chemistry. If you're in space or in a vacuum, it's a different story. In contrast, tertiary carbocations are reasonable intermediates in organic reactions in solution because they're stable enough to be observed. And in fact, the biosynthesis of cholesterol involves a ton of tertiary and secondary carbocationic intermediates. So I guess we can draw the secondary carbocation here and the primary carbocation here. And stability decreases as we go from tertiary to primary. All right? So what does that mean for our diagram here? That is, if we go from primary to secondary to tertiary carbocation, we're going to lower the energy of the carbocation. We will also lower the energy of the transition state, and then the transition state will go through these points, and the SN1 reaction will be faster. All right. So you could memorize carbocation stability. You could memorize that trend. But it's really useful to know why it's the case so that you can spend less of your 3 hours looking stuff up and more of your 3 hours thinking through problems that you can solve. So let's talk about carbocation stability. The reason for this trend has to do with hyperconjugation, which you're going to feel like by the end of 351 is the answer for everything. And it's not. That's the number 42 or something. Maybe it's 43. I can't remember what. I've never actually read the book. But in any case, it's the answer to a lot of things in organic chemistry. And I believe this example should be familiar to you because when we first learned about hyperconjugation and considering why staggered is more stable than eclipsed, I believe we used a carbocation as an example. So I'm just going to draw a primary carbocation. All of these atoms that I've drawn so far are in the plane that's indicated by that gray parallelogram. Here is the positively charged carbon. Here is a carbon-hydrogen bond in the plane of the page and coming up out of the parallelogram plane, and then these two carbon-hydrogen bonds would be going out towards us and back into the page. But the atoms that are highlighted in gray would be the ones that are all in this plane. Okay. Now, if I were to ask you what the LUMO of the carbocation is, you would have told me, hopefully, that it's the empty p orbital on the positively charged carbon. And we would have maybe drawn that empty p orbital like this. We'd fill in color for wave function sign, just to indicate that there's a switch in wave function sign as we go from one lobe to the other. Wave function is 0 in the plane of these carbon and hydrogen atoms. Whoops, what the heck is that? And one of the things we've talked about previously is how an adjacent carbon-hydrogen bond can line up with that empty p orbital. So I'm going to draw a carbon-hydrogen bond for you, except I didn't like that. It basically has a large lobe that encompasses the hydrogen and then a smaller lobe on the back side. And that filled sigma bond, carbon-hydrogen sigma bond, can line up with the empty p orbital, be eclipsed with the empty p orbital, as it were. And when that happens, they can mix together to form new molecular orbitals. Now I'm going to try something totally superfluous, and that's to color in the, except that's too big. No. Gratuitous waste of classroom time for coloring. All right. So when we mix the sigma carbon-hydrogen sigma bond with the empty p orbital, remember the math of MO theory makes us do that in plus and minus senses. The plus sense is always lower in energy, and let me draw what this looks like. It basically looks like the drawing I've done up here, only I'm going to show you, I'm going to illustrate it a little bit more realistically. The electrons in the carbon-hydrogen bond spread out a little bit onto the adjacent positively charged carbon. And because they are spread out, they are lower in energy, and also they get to experience 2 or 3 nuclei instead of just 2. And from a certain perspective, as you look at that plus combination, it almost looks like a sigma bond that's trying to lean over and be a pi bond a little bit. The minus combination is the other consequence of hyperconjugation, and that is that we spread out the empty p orbital onto the adjacent carbon. And so what does this look like, or to the adjacent carbon-hydrogen bond? What does this look like? Well, you still have, the Lumo is still mostly the p orbital. But then some of it's out on that adjacent carbon. There's a node in between the 2 nuclei to reflect the fact that this is the minus combination. And for filled orbital interacting with an empty orbital, who cares about the higher energy orbital, because we've spread these electrons out, they're lower in energy. It will be important to us later, though, to remember that the Lumo is not only on the positively charged carbon, but also on the adjacent hydrogen. All right. So that's hyperconjugation. There's more opportunities for hyperconjugation for tertiary carbocations, because there's simply more adjacent alkyl groups. And in the methyl carbocation, there is no hyperconjugation. There's no adjacent carbon-hydrogen bonds that can line up with the empty p orbital. Great question from Taylor at home. Does hyperconjugation make that adjacent hydrogen more acidic? Yes, it does. A reveal that won't matter for this exam, but will matter for the next, is that if you have a carbocationic intermediate, whatever nucleophile you use really can't be selective for carbon versus hydrogen, and you'll get products from attacking carbon at the same time as you get products from attacking the hydrogen. We'll get there, but yeah. And then Marianne, you asked, where did I say the LUMO was? The LUMO is mostly the empty p orbital, but a little of it is on that adjacent carbon-hydrogen bond. Okay, other questions? So that's the why, for why tertiary carbocations are more stable than primary carbocations. So now let's compare. The drawing we made last time was basically for a methyl halide. This was basically for methyl iodide with some nucleophile. And it was a good nucleophile. It was on our list. I believe it was cyanide. So let's copy all of that and let's adjust the diagram for using a tertiary alkyl halide. And let's just see if we can sort of predict what happens and how the energy diagram changes. I'm going to have to erase a bunch of stuff. Sorry. In fact, maybe we should have just redrawn it. Close enough. All right, so let's start with the SN2 transition state. And we'll use the blue dot to indicate, fine. We'll use a blue dot to indicate where the transition state initially was. And then let's use the black dotted line to indicate that we are going from primary to secondary, going from maybe methyl to primary to secondary to a tertiary alkyl halide. And that, because of sterics, should increase the energy of the transition state for SN2 to the point that it no longer becomes doable. The transition state is high enough in energy that the activation energy for that SN2 step is too high to occur at whatever temperature we're thinking of. So now I'm going to erase this line and draw a new one going through that high energy transition state. Maybe we'll complete the shading there. Okay, so in effect, we made the pathway for SN2 harder to get over. I'm going to use purple dots for the transition state and for the carbocationic intermediate. I'm going to erase some of these lines now. We said that as we go from methyl to primary to secondary to tertiary carbocations, that we're going to go more stable. So that should lower the energy of the starting, or I'm sorry, the carbocationic intermediate. And that should also lower the energy of the transition state that leads to that carbocationic intermediate. So now it's actually, oops, I'm going to miss. Now it's easier to get over the transition state for the SN1 reaction and then downhill to the products. So this is the situation, and this is how it's changed when we change the character of the alkyl halide. As we go to a more substituted alkyl halide, it becomes easier for us to go over the SN1 barrier to the carbocation and then down to products, and more difficult to get over the SN2 barrier. Okay, so to summarize what we've done so far, this is sort of everything we know about these two reactions. Nope, not that. We know that good nucleophiles prefer SN2. They will wait for SN1 if they have to, that is, if you're using a tertiary alkyl halide. Weak nucleophiles don't do SN2. They're not reactive enough. And then the ability to do SN2 versus SN1 also depends on alkyl halide structure, where SN2 is fastest for primary and slowest or not observed for tertiary, and SN1 is just the exact opposite. So with those principles in place, you can predict what's going to happen. But before we do that, we need to talk about how you even know these mechanistic details in the first place. How could you tell whether a reaction was SN1 versus SN2? You could do the kinetic experiments, and that's always a good idea. But the SN2 and SN1 reactions have distinct stereochemical consequences. Stereochemical consequences of reactions, really important in 351 and again in 352. So it's worth paying attention to and worth mastering. Recall that we said that the SN2 reaction, and I'm going to draw a secondary alkyl halide, and I'm going to use a good nucleophile here, and this is from our list of good nucleophiles last time. Recall that we said that the nucleophile attacks from the backside because that's where the LUMO, or the carbon iodide sigma star, is. That LUMO looks a little bit like this, with a node in between, a large lobe on carbon and a large lobe on iodide. We've already talked about why you attack at carbon versus iodide. We're going to use blue to indicate places where the wave function changes sign. The nucleophile attacks from the backside because that's where the LUMO is. You dump electron density into that antibonding orbital and you break the bond. We call this backside attack. Now, as the nucleophile starts to approach and the leaving group starts to leave, we're going to see the substituents on the carbon that bears the leaving group are going to be repelled away from the incoming nucleophile. And as the leaving group leaves, they're progressively going to take up space that used to be taken up by the leaving group. So you may recall that the transition state that we've drawn for this SN2 reaction almost looks as though we have a planar carbon at the middle of it. You have iodide having left, and you have the new nucleophile coming in, and you have partial negative charges on both. As we continue to progressively form this new bond, the groups that are on that central carbon are going to continue to be pushed away from the incoming nucleophile. And in the product, we're going to see that the nucleophile came in and attached itself to the opposite side of the molecule to where the iodide used to be. Okay? This may be easier, this switch may be easier to see, if we draw the molecule in a slightly different way. In the product, would look like this. And if you don't believe me, you can go in and assign R versus S here and confirm that it's the same here. The stereo center in the iodide would be, S. And in the thiol, the stereo center would be R. We call this process inversion of configuration. And I hesitate to summarize this as S turns into R always, R turns into S always, because it will, of course, depend on the priority of the group that used to be there versus the priority of the group that you put there. In this case, we swap out iodide, which was the highest priority group, for the thiol, which is sulfur, which is also the highest priority group. And so it does cause a change from S to R. But what we mean is that the nucleophile replaces the leaving group from the other side of the molecule. In the drawing below, iodide used to be up. The nucleophile that came in is now down. This is a universal consequence of the SN2 reaction. This is how it happens. And indeed, if you start out with a chiral starting material and it's only one enantiomer, you only have one of the two enantiomers, and it is pure, when you do the SN2 reaction, the product also is chiral, is also one enantiomer, and is also pure. Stereochemical information in the starting material for that stereocenter is still in the product. We've switched configuration, but we started with a stereocenter and we end with a stereocenter. And this, we have a term for this in chemistry that you'll see come up a little bit. We call this reaction stereospecific because the mechanism requires this stereochemical consequence. All right? So if I gave you this, a related problem on an exam, let's just change the leaving group and let's change the nucleophile. If I gave you this question and you saw this is a secondary alkyl halide, so you went up and you reminded yourself that SN1 and SN2 are both possibilities for secondary alkyl halides, so then you consider the nucleophile. You remind yourself that cyanide is a good nucleophile, so you conclude that the mechanism is SN2. If you concluded that and drew this option, that would tell me that you do not understand what the term SN2 means, or that if you do, you don't understand its stereochemical consequences. Because this is not the SN2 product. There's no way to get that in a one-step SN2 reaction. You might also be tempted to say, to hedge your bets and say, well, just for fun, I better do both enantiomers. That is also wrong. That is not a consequence of the SN2 reaction. The SN2 reaction does not take a chiral molecule and turn it into a racemic mixture. No, the only correct answer here for the SN2 reaction, the only answer that demonstrates mastery of what the SN2 reaction is this one, inversion of configuration. Okay? All right, questions on that? Yeah?
I still don't understand why the first one isn't correct.
It's the wrong enantiomer. So the question is, why isn't this first one correct? Bromo was up. If the nucleophile comes in from the backside attack, from the backside to attack, it must be down. Yep. So watch for that, because that's an easy mistake to make. It's also a very easy mistake to fix once you know the principle. So don't let this happen to you. All right. Yeah.
With the SN1 reaction, could you get the opposite enantiomer as well?
For the SN1 reaction, would you get the opposite enantiomer as well? Well, let's talk about that. Why do you propose that?
Well, because I'm just trying to think out loud as I'm going through this, but it doesn't have to always backside attack.
Right.
Because they're not coming in and going out at the same time.
Okay.
So then you might get both enantiomers as well.
Okay. Yeah, in class, we've just been discussing how whether or not if it was SN1, you might get both enantiomers. And the interesting statement here is because the leaving group is not leaving at the same time as the nucleophile comes in, maybe you don't have to just attack on the backside. So for this same starting material, this chiral pure alkyl bromide, it's a secondary alkyl halide, so we go back and remind ourselves that both SN2 and SN1 are possible. So we go look at the nucleophile. We see in this case the nucleophile is methanol, which is a weak nucleophile. So we decide the mechanism would need to be SN1. The first step of SN1 is leaving group leaves. Once that leaving group leaves, remind me about the geometry of the resulting intermediate about that carbon. What's its hybridization? What's its shape? sp2 planar. By the way, it's now also achiral or not chiral. We lost the stereocenter when the leaving group left. The top face of the molecule is exactly the same as the bottom face of the molecule. So our nucleophile can come in from above or below with equal frequencies. So yes, we're going to get both enantiomers. We're going to get the enantiomer that comes from methanol attacking from above, and we're going to get the enantiomer from methanol attacking from below. Because I've used methanol as a nucleophile, after it attacks, I've got a positively charged oxygen in each of these enantiomers that's attached to three things. What likely happens at this stage is methanol is our solvent, and additional methanol molecules by Le Chatelier's principle remove the proton from there, and you end up with your final product, the neutral, and I guess the functional group we just made is an ether. Don't worry too much about this proton transfer step I just drew. The important point is we get both enantiomers from the SN1 reaction. And this is why above that was not a right answer, because if you draw both enantiomers, that communicates that you think you went through an SN1 mechanism. All right, I guess that's out of time for us today. I'll catch you again Friday.